Welcome to Programmers Podcast number 85, and today we're talking about the Lattice Boltzmann Method for CFD. Now, if you haven't heard of this, it's sometimes goes under the Lattice Boltzmann Method, LBM, Lattice Boltzmann Method, CFD, etc. If you haven't heard of this, it's probably for good reason, and the reason is because it's not very mainstream at all. In fact, almost no one uses this for their research or work for industry, but it's fairly new and it has huge potential. I'm a huge fan of the LBM method, the LBM CFD, and I came across this about 12 or 13 years ago, something like that. And as I mentioned, no one uses it. So let's talk about what this is and what the potential future holds. So this is not going to be a podcast on the equations of it. We're going to go through the application of it. The reason why I don't want to do this podcast to do with the equations is because I want to do another podcast, maybe a podcast series on that, because it is very interesting. So let's talk about CFD and how this fits in. So up until now, so like for the last 30 years at least, whenever someone said CFD, we always immediately think we're using Navier-Stokes equations. So we're using RANS, URANS, DES, LES, DNS. And that is for good reason. That is because the Navier-Stokes equations up until now have provided a very good method of simulating flow. They're far better in terms of the accuracy compared to like potential flow solvers or the elliptic line theory, which is very old but still quite a nice little tool if you know how to use it properly for certain applications. But CFD now is definitely dominated by Navier-Stokes equations. However, there is a new method which is, in my opinion, better and provides more promise than Navier-Stokes equations. That is the Lattice Boltzmann method. So let's talk about these two different methods. So up until now, the Navier-Stokes equations, they use these equations, which are effectively four equations, with three for Navier-Stokes and then one with continuity. And what they do is they look at the flow from a sort of macroscopic point of view. So you get your flow and you divide it up into cells, and in each cell, you calculate the velocity, the density, and the pressure. And these are all macroscopic properties for this cell in general. And this is a very powerful tool, and CFD is done very nicely using Navier-Stokes equations. However, there are some disadvantages to using Navier-Stokes for CFD, and we're seeing them now. So one of the major disadvantages is that it doesn't scale very well. And that means that when we try to solve very complex flows or very computationally expensive flows, our main go-to method is just by using more cores, using more CPU, using more computational power. However, there's a limit to that because if you, let's say, have one core or one thread or whatever you want to call it, I usually say core. So if you're not used to that terminology, let's just think of it as like a CPU. So if you use one core to simulate a flow, and it might take 20 hours. Now, if you want to speed that up, you can say, okay, I want to use two cores now. So I've got two cores on my computer. I want to put both of them onto my CFD. Now, you might expect it to be only take 10 hours to solve, but in reality, it's going to be more like 10 and a half, 11, 12 hours to solve. It's not going to be a 50% reduction, even though you have twice as many cores. The reason is because the way that the simulation is set up is that it divides these cells up. So each core is taking up working on different cells, but there has to be communication of the information of these cells between these two cores. So you calculate, let's say, group A with core 1 and group B with core 2, and group A might have all these different pressures and velocities and whatever, and turbulence and whatever you're calculating. And some of the cells in group B might need that information. So you need to transfer this information. So you might have a 40% reduction in computational time instead of 50%, as you might want. So to speed this up, you go, okay, I'm going to use 4 cores. I'm going to double that again. But instead of going to 6 hours, it might take 8 hours. So again, you only get a slight reduction. And the further you go, the lesser reduction you get. So once you get, in my experience, once you get to about 2,000, 3,000 cores, you don't get any more benefit in terms of time for solving. So that means that you have a limitation on how many cores you can use to solve your equation, which means that you can only really, your CFD, which means that you can only really speed up your simulations so much. That's where the Lattice Boltzmann method comes into it. So this is the major selling point of the LBM CFD approach, and that is that it scales far more linearly. So let's start off with our basic set up again, where we have our simulation and we are running it on one core, and it takes 20 hours. Then if you run it on 2 cores, it might only take 10 hours and a couple minutes. And then you run it on 4 cores, it might take 5 hours and a few minutes. And then you run it on 1,000 cores, and it reduces it by the equivalent of 99.9% or 99.8%. So it scales very linearly, which means that we are no longer hampered by this limitation in cores that we can use, and that is very beneficial. So that's where the Lattice Boltzmann strength comes into it, and it's a major strength. There are other strengths as well. There are weaknesses as well, which is why I want to do a whole nother podcast or podcast series on those. But that's the idea. So how does this happen? How is the Lattice Boltzmann method different to Navier-Stokes? So I mentioned we use the Navier-Stokes equations for the Navier-Stokes CFD. For Lattice Boltzmann CFD, we use Lattice Boltzmann equations, and this is so there's a bit of a misconception out there to some extent. So the main way of explaining the Lattice Boltzmann method is that instead of looking at the macroscopic level, you look at the microscopic level. So you look at each particle. That's not strictly true though. You're not looking at each particle. What you're looking at is the flow from a particle point of view, but you're not looking at each particle. That's an important distinction to make. So what we actually do is we get our flow again, and we split it up linearly, effectively. And we'll get into a little bit more about this later. I'm just giving you a general idea. So let's say you have a flow which is 1 meter long, and you want to split it up into 10 points. So that means each point is going to be 0.11 meters spaced. So 1 divided by 10 or 1 divided by 9 plus 1 cell or 1 point at the start. So that means 0.11 meters, so 11 centimeters. So they're linearly spaced, and you're looking at what the properties of the particle at each one of these points is, and then you're saying, okay, so the particles at these points are this. So it's sort of an average, and this is what's called a mesoscopic scale. So it's not microscopic, it's not macroscopic, it's in between. And this is how it differs to the Navier-Stokes equations. Now, theoretically, I guess you could make the grid so fine that you're looking at every particle. However, there are some limitations to that with the Lattice Boltzmann method, and that is because the grid is usually linearly split up. It's not, you can't really have refinements, at least not yet. There are some programs that are looking into the refinement zones, but generally speaking, the entire simulation that you have will be uniformly divided. So that's very different to the Navier-Stokes CFD, where you can refine certain areas, you can put boundary layer meshes, and that's a very powerful thing that Navier-Stokes CFD does have. So that's the general idea of the Lattice Boltzmann method. Oh, sorry, I should also mention what properties they're calculating. So where the Navier-Stokes equations are calculating the macroscopic properties such as density, pressure, and even velocity, the Lattice Boltzmann method is calculating the actual microscopic properties, such as just the velocity. And then from there, you can calculate what the pressure and the densities are from knowing these microscopic properties. That's how this works. They're using different equations. So that's a general crash course in how the Lattice Boltzmann method differs to the Navier-Stokes method. And let's get into whether this method is actually good or not, and at what the state is at the moment. So to do that, we're going to look at a paper called Application of a Lattice Boltzmann Method to Some Challenges Related to Micro-Air Vehicles. And we'll go through why this is important and how the Lattice Boltzmann fares. So just a warning, this is probably going to be a 2-part podcast series because I like Lattice Boltzmann's method so much that I'll talk about it a lot, as you can already probably assume. I've already gone on about 8 minutes just talking about the general idea of it, and there's so much more to talk about. So let's get started. So low to moderate Reynolds number flows, typical of MAVs, so between 1,000 and 100,000 Reynolds numbers, tend to promote flow separations that decrease efficiency and lift, which are difficult to predict with classical computational fluid dynamic methods such as the RANS approaches. And the reason why these low to moderate Reynolds number flows typically promote flow separation is because the flow doesn't have much energy at these low Reynolds numbers, which means that it can detach much easier. If you don't know why that is, check out some of our other podcasts on wings, and I go through it a bunch of times. So with the increase in computational power, large eddy simulation emerges as a promising technique to improve the reliability of flow solver predictions. Several works have already shown that the LAS approach leads to significant improvements both in the understanding of flow physics and the performance predictions of rotors. Usually, LES is based on the resolution of the filtered Navier-Stokes equations. So what this means is that if you're not familiar with LES, you're just looking at the large eddies and not looking at the very finer scale things. And with the finer scale things, you just use modeling. So while effective, this method requires the use of artificial dissipation, which limits its accuracy. For example, transport of turbulence on a long distance, noise reduction, etc. So what this means is that you're effectively modeling these things, and like anything, if you're just using a stochastic model or empirical model, or you want to call it, there are errors associated with that. Now, the Lattice Boltzmann method, or also known as LBM, is a recent and more popular alternative to Navier-Stokes solvers. Now, I should mention that this more and more popular alternative, I should stress the more and more popular, because it's definitely not popular at all at the moment. Like, in the world, there's probably only like 500 people who are working on it, whereas like there are hundreds of thousands of people who use Navier-Stokes flow solvers. So that's how niche LBMs are at the moment. I just wanted to stress that, so you don't feel like you're missing out on something at the moment, because it's not that common. I just wanted to make you feel better about that. So instead of directly solving the Navier-Stokes equations, this method, the LBM method, tackles the Boltzmann equation, a statistical equation for the kinetics of gas molecules, so how gas molecules are moving on their microscopic levels. So thus, the primitive variables of the LBM represent a statistical particle probability distribution function, to which the usual macroscopic variables such as pressure and velocity relate as velocity moments or as observables in the sense of statistical mechanics. So again, they're looking at each of these particles from a statistical point of view and in the microscopic point of view. The particle distribution is a continuous quantity. In contrary to popular belief, the LBM is a continuum method and not a discrete particle approach. As I mentioned earlier, this is one of those misconceptions that are a little bit out there, where you're not looking at each individual particle, you're just looking at particles in general. So you're calculating general particles, but you're using the microscopic variables. Indeed, the method offers an Eulerian view of the flow and is mesh-based. To illustrate the advantages and drawbacks of LBMs, 3 applications have been selected in line with the MAV challenges. So a direct numerical simulation of a single blade rotor at low Reynolds numbers, an LES of an rotor operating in ground effect, and an LES of a rotor optimized for acoustic performance. I should note that direct numerical simulation is still pretty much beyond us at this point in time. So that's why they use LESs for more complex flows and faster flows. So let's talk about the LBM approach just generally. The Lattice Boltzmann method considers a discrete Boltzmann equation, a statistical equation for the kinetics of gas molecules, instead of solving directly the Navier-Stokes equations. Now, I should also mention that the Navier-Stokes equations are actually somewhat of a simplification of flow in general. So they don't take into account acoustics, they don't take into account the thermal aspect. So they are simplifications. But for CFD in general, for aerodynamics, they are pretty decent. They're actually very good. Lattice Boltzmann method, though, actually doesn't have these limitations. So they do technically contain more information if you want it. So the primitive variables of the LBM represent the statistical particle probability distribution function, to which the usual macroscopic variables such as pressure and velocity relate as velocity moments. In that regard, the particle distribution function is a continuous quantity and not a discrete particle approach. Beyond its computational performance, the main advantage of LBM is that the method is stable without artificial dissipation, which was one of the drawbacks for Navier-Stokes. Its drawback is that it requires the use of a Cartesian grid, which dramatically increases the number of grid points necessary to compute the flow close to the walls. So this is what I mentioned earlier, where LBMs at the moment do not allow refinement zones. Now, I should mention, this paper was written in 2018. I was recently watching some lectures of this group from Geneva, and they developed this code called Palabos, and they are looking into these refinement zones. Now, at the moment of this podcast, I'm not sure how far along they are in terms of implementing that in their actual code, but I know that they are researching it. So when they're saying that this is one of the drawbacks, I believe that this is a drawback that will be solved quite quickly, at least not in the distant future, in the near future. There are other drawbacks for the LBM method, for the LBM approach. And there are some arguments that can be made about it's been oversold in some senses, but even though it has been oversold in some cases, for example, one major drawback of the LBM approach is that the time step that you specify is usually implicitly specified. So you can't really specify explicitly. At least that's one of the problems at the moment. But I think that will be solved as well. So that's why the LBM approach has such huge potential. It reminds me a lot of the early days of CFD, of Navier-Stokes CFD, where there were lots of problems, but they've been ironed out one by one to the point where now we can get very good approximations for pretty much any flow, really. And the same thing will happen with the LBM. The major benefit of LBM is that you can solve it much quicker. So depending on the target in terms of the Reynolds number, the turbulence can be fully simulated, so DNS, or only the largest scale can be simulated while the smallest ones are filtered, so LES. Due to the filtering provided by the regularization step, the use of subgrid scale model is not necessary. So the Smagorinsky model, for example, the LBM equations are solved using the open source software Palabos. They use that in this paper as well. It's it's probably the most common open source LBM software at the moment. The other one would be OpenLB as well, which are both based on the same libraries, like they come from the same root. So let's talk about how the LBM approach fares compared to the traditional Navier-Stokes CFD. The first one is a single-bladed rotor at low Reynolds numbers. So this is the DNS approach, as we mentioned earlier. The first application deals with development of bio-inspired nano-flying robots. At very small scales, the observation of nature suggests that flapping wings may be a relevant solution to performing both hovering and forward flight with enhanced maneuverability. They say that although there is no compelling evidence that flapping wings are more aerodynamic efficient than other hovering capable concepts, in particular rotating wings, flapping wings have gained considerable attention due to its unique flow features upon which it relies. Now, I would sort of disagree with this. I think there is significant evidence indicating that flapping wings are more efficient and better. One of the major piece of evidence for this is when you look at the insects and birds with flapping wings. I've done some podcasts on this. You can find it on YouTube. But if you look at some of these insects and birds, their payload that they can carry compared to their weight is huge. So that's one major piece of evidence indicating that flapping wings are better than rotating or even fixed wings. In this case, I'm talking about rotating wings. So one of the unique flow features of flapping wings is that the development of a large-scale leading-edge vortex, wing-wake interactions, and other unconventional mechanisms such as clap and fling, depending on the precise kinematics of the flapping wing. So clapping and flinging up of butterflies, for example. Again, I've done some podcasts on those. Among these mechanisms, the development of an intense conical leading-edge vortex has proven to be the predominant mechanism at the play for the generation of strong aerodynamic forces. The dynamics of the leading edge vortex can be investigated by looking at a single stroke of the whole flapping cycle. Now, just briefly, the leading edge vortex is a major component of the lift generation mechanism for insects and birds. And it's very contingent on how fast you flap. So if you flap too fast, you won't get nearly as much lift. If you flap too slow, you won't get nearly as much lift either. There's a real optimal range there. In this section, a direct numerical simulation of the flow is performed past a single stroke of the flapping cycle, which is here modeled by a wing revolving at constant speed about its root. And then they have figure 1, which has the comparison of the lift coefficient between the Lattice Boltzmann approach and the DNS with Navier-Stokes. And they have two different DNS Navier-Stokes results, one from one group called Galdo and others, and Jardin and David. And so in figure 1, they say the main characteristics of the blade are summarized in table 1, and the wing has a rectangular platform with an aspect ratio of 4. It revolves at a constant speed about its root through 180 degrees. The blade angle is set to 45 degrees. The Reynolds number based on the revolving speed and the wing chord at the tip is 1000. And figure 1 shows instantaneous lift coefficient. The results are compared with the literature, and they say that it shows that the results obtained from the LBM approach match those obtained with other well-validated methods within reasonable accuracy, within 3%. 3 grids have been designed with resolutions of 0.015 of the chord, 0.012 of the chord, and 0.11 of the chord. So in other words, they looked at the Lattice Boltzmann method, they compared it to Navier-Stokes CFD. First of all, they found that the instantaneous lift production mimics very closely the instantaneous production that they found from other CFD methods. However, it's just offset by 3% for some reason. So that's quite interesting. They also looked at refining the grids to see how the grid resolution, as you do with Navier-Stokes CFD, affect the lift production. And they looked at 3 different resolutions. They said that converged lift is achieved for resolutions finer or equal to 0.012 of the chord. Indeed, while approaches by Mengaldo and others, and Jardin and David, demonstrate mesh dependency for cell sizes on the order of 0.015 chords, the present Lattice Boltzmann approach requires space resolutions in the order of 0.12 chords. So what does this mean? So in other words, for the Navier-Stokes CFD, they could get away with a more coarse mesh than the Lattice Boltzmann method. Why would that be? One reason that I can think of, actually there are 2 reasons. One of the major reasons is that you don't have the mesh resolution ability with the Lattice Boltzmann approach. So what that means is to get finer resolution around the wing, you need to make the entire domain finer. That's a major limitation. Whereas with CFD, with the Navier-Stokes approach, you can then just specify different resolution areas so you can refine near the wing a bit more. That's very beneficial. The other reason why potentially they needed a finer grid is that the time step. So the grid heavily determines what the time step will be for the Lattice Boltzmann method. So to get the right time step, they needed to reduce the grid resolution. That's another potential reason. I'm not sure what the reasons were. They didn't get into it in here. I'm not sure if they found them, but those are 2 potential reasons based on the Lattice Boltzmann method. So in figure 2, they show the isosurfaces of the Q criterion obtained from the Lattice Boltzmann simulations, so that what they're showing are the vortices around the flapping wing. They say that figure 2 shows the sustained lift is correlated with the development of a stable leading edge vortex on the upper surface of the wing, and that agrees very well with theory. So that's what they found with Lattice Boltzmann as well. The leading edge vortex develops during the initial stages of the revolving motion, but rapidly reaches a stable state, i.e., it does not shed into the wake, hence generating high aerodynamic forces. Recent studies suggest that leading edge vortex stability is promoted by rotational effects and is therefore inherent to low aspect ratios of the revolving and rotating wings. Present results further show that the conical leading edge vortex bursts into small scale structures at the wing tip, in agreement with experimental observations, highlighting the capability of the present Lattice Boltzmann approach to tackle the onset of chaotic turbulent flow. So in other words, they're saying that experiments and literature to date have shown that this leading edge vortex occurs and it breaks down the wing tip into turbulence quite readily. The Lattice Boltzmann method also showed this. So this is showing that the Lattice Boltzmann method is very capable of doing what we need it to do. It's still quite accurate. So this is good news for it. So in figure 3, we're talking about the 2-blade rotor in ground effect now. So this is a more complicated situation. Instead of just one wing flapping up and down, you have 2 rotors going around, and they're using LES here, not DNS. LES is not as accurate as DNS. So this application, figure 3, this application targets the prediction of the turbulent flow produced by an MAV rotor interacting with the ground at moderate Reynolds number, so 100,000. The main parameters of the configuration are summed up in table 2. So let's roll to table 2. So the rotor is composed of 2 untwisted flat plates with a radius. This is interesting because often actually on rotors, you twist the rotor to change where the lift is being produced and make the rotor more stable at faster speeds, or even more to produce more lift across the rotational speed spectrum. But these are untwisted flat plates, and they had a radius of 0.125 meters, so 125 mil. The chord of the blade is set to 25 millimeters. The pitch angle of the blade is set to 15 degrees. The rotor is located at 2 radii from the ground, corresponding to 2. So, an overview of the flow produced by this configuration is shown in Figure 3. Figure 3 shows instantaneous flow field, the velocity. Now, interestingly, from the probably about from 10% from the wing root, you have a lot of flow being pushed down, but at the wing the rotation axis, that center, there's actually some flow going up, which is normal for rotating propellers. So the wake generated by the rotor impacts the ground and is progressively deviated towards the outside part of the domain, a boundary layer that then develops at the ground level. Such a flow impacts the operability of MAVs using propellers and can limit the emission that can be achieved, especially in highly confined environments. An accurate description of the rotor wake in ground interaction requires use of complex methods such as an overset mesh. So the overset mesh is where you have the global mesh, then you have, let's say you have 2 objects and they move in relation to each other over time. So with a traditional mesh, these objects have to be fixed in space because you can't move them. Like once you mesh them, that's the mesh. But with an overset mesh, what you do is you get one object, you put an additional mesh over it. That's called a local mesh. And so you have the global mesh with this local mesh over the top, just localized to this little area. And as this object moves through time and space, this mesh will then move along with it. And that way you can have these objects moving together. And what happens is you calculate the properties at the global level and the local level, and then the local level you print onto the global level. That's just the general idea of an overset mesh. The main objective of this application is to validate the capability of the Lattice Boltzmann method to reproduce the flow generated by such in-ground effects by comparing this with the experimental data. To study the sensitivity of the solution to the grid, 3 meshes are used to perform the numerical simulations. For each grid, the resolution is increased by a factor of 2 compared to the previous grid. So this is important because even though the resolution is increased by a factor of 2, that actually means you have a factor of 8 times the number of grid points. The reason why is because you have 3 axes. So yeah, you make one axis finer by a factor of 2, the other axis by a factor of finer of 2, and then the third one finer by a factor of 2 as well. So it's 2 to the power of 3, which is 8. So you get a lot more grid points. The resolutions compared to the rotor chord are respectively 0.1, 0.05, and 0.025. So the rotor diameter is described respectively by 94 points, 188 points, or 375 points, depending on the grid resolution. The total number of points is respectively, so this is a lot, either 131 million, 13 million, 105 million, or 830 million, which are a lot of grid points. And this is, again, one of the benefits / one of the detriments of the Lattice Boltzmann method, depending on how you look at it. One of the benefits is that because the Lattice Boltzmann method is more efficient in terms of computational power, you can use more grid points and do more interesting things. The downside to this is that because you cannot resolve certain areas, you need to put more and more grid points in just to get a stable solution or a good solution, which means you need to have more cells. So that's one of the downsides. So these are 3 different grids that they used. Figure 4 is a comparison of the time averaged flow fields obtained with the 3 grids to show how it converges. Regarding the convergence of the flow close to the ground, the numerical simulation on grid 0, so the coarsest one, is not able to reproduce the interaction of the rotor wake with the ground. The main reason is due to the underprediction of the rotor thrust, which results in a lower velocity at the rotor outlet and a dissipation of the wake before it reaches the ground. Results on grids 1 and 2 are in reasonable agreement, but discrepancies are observed in the rotor wake, where the peaks of the velocity are underestimated with the second grid. So this qualitative comparison shows that the obtaining of grid independence results remains a difficult task with pure Cartesian grids. So in other words, in this particular case with a rotor with 2 blades rotating around, the LBM method, the Lattice Boltzmann method, did not perform adequately compared to the first simulation that we saw. The reason why is because of the Cartesian grid, as I mentioned. So as we've mentioned earlier, you can't really refine very easily, and that's a major limitation in this case, resulted in okay agreement, but not very good agreement. So that's one major weakness. So they then looked at figure 5, which is the experimental data of Jardin and others, and they compared to the numerical predictions of the LBM approach with the finest grid. And they give the time average velocities. So the comparison is shown in figure 5a and figure 5b. This comparison shows the LBM correctly reproduces the time averaged flow in the vicinity of the rotor wake. So not near the ground, but near the rotor wake. The discrepancy with measurements close to the rotor axis is mainly related to the presence of the motor that is excluded from the numerical simulations. At 0.5 by 50% away from the rotor, so approaching the ground, so you're going down a little bit, the Lattice Boltzmann CFD underpredicts the peak velocity by 7%, but the thickness of the rotor wake is well predicted, included far from the rotor. The interaction between the rotor wake and the ground drives the development of a ground boundary layer. So in other words, it's getting the LBM approach is getting the general flow physics right, just the magnitude is a little bit off. But considering that there was that grid problem, it's pretty decent for a first try, I think. The velocity magnitude is shown in figure 5b at 2 locations. So two locations downstream of the rotor. The LBM method, the LBM CFD, sorry, is in good agreement with measurements, especially close to the ground, at a distance of 1 rotor diameter down underneath the rotor. The LBM underpredicts the peak velocity by less than 5%, and the location of the velocity peak is shifted slightly compared to the experimental data. At 2 rotor diameters underneath the rotor, the thickness of the shear layer is well produced by the LBM approach, and the peak of velocity is also slightly underpredicted by 7%. This quantitative comparison demonstrates that the LBM approach on the finest grid is able to reproduce the complex flow field generated by the interaction between a rotor wake and between the rotor and the ground. The conclusion of the second application is that the LBM approach successfully reproduces the flow generated by the rotor ground interaction, which is validated by comparison with experimental measurements. So that's the second of the 3 comparisons. This is where I'm going to end this podcast because I've noticed I've just gone 35 minutes or so. In the second podcast, I'm going to look at the third validation study, as well as some aeroacoustics, which is very interesting. This is one topic that traditionally Navier-Stokes CFD has fallen short on. That's mainly because people use RAND instead of LES and DNS, but it's still important in terms of from a practical application. So we will see whether the LBM approach is good for aeroacoustics as well. So far in this paper, we've seen that the LBM approach is pretty good in terms of the qualitative flow features, and to a certain extent the quantitative flow features as well. And the reason for these discrepancies in the quantitative approach could be due mainly to the grid resolution, which is, again, it's often sold as a feature and as a benefit, but sometimes it's detrimental. Like they say LBM approach, you can use more cores, so you can use more cells and get a more accurate solution. But at the same time, you need more cells to get an accurate solution compared to a Navier-Stokes approach. So that's something that I want to get into in other podcasts, as I mentioned, some benefits and detriments. So that's in this podcast. In the next podcast, we'll pick up where we left off here with a third case and aeroacoustics. So make sure to like, subscribe this, and check out our Atmosphere Hawk, which is an instrument we make to make your experiments 2 to 4% better, and it'll make your CFD more accurate, including if you use LBM as well. I hope you do use LBM because I'm really excited about LBM. I know I'm probably an early adopter in this case, but it's really cool, and that's why I want to do more podcasts on it. And if you want to check out LBM as well, check out the next podcast as well, and we'll probably talk about it a lot more in the future. So make sure to like and subscribe, and check out our CFD courses, link in the description. And I'll see you next podcast. Peace out, amigos.